This will be our first look at a video that you guys would watch in class or to help you review. We're just going to get the ball rolling. This is going to be associated with the first 4 pages of notes in the course. So we're going to try to understand some of the basic terminology of probability. A lot of this will be familiar to you, and then calculate some probabilities using multiplication, addition, and what's called the complement property. So let's start similar to what we did kind of in class, flipping a coin. And we looked at just imagining what this would look like, and then we looked at a better way of doing it, probably, which is some type of simulation. But we could actually use our calculators to simulate this, and I'm going to show you how in just a minute. So let's define our event. So we'll say we want heads or tails, assigning random numbers to the events. So using the calculator, we could say 0 to 4 will be heads, 5 to 9 will be tails. Even heads, odds, tails. Right, we're splitting it in half. Well, that's because on most coins, you got a 50-50 shot, heads or tails. It's a fair coin. Probably the easiest way to do it would probably be using digits 1 and 2. And I'm going to show you how to do that here in just a minute. Let's say that we want to say 1 is heads and 2 is tails. Let's say that we'd like to do 5 trials. So one way we might see that written, it'll be the number of trials. We'll try 5 flips of a coin, or we could say we're going to flip 5 coins at one time. Either way, we're talking about the same thing. Then we execute the simulation. So if you go into your calculator, if you hit the math button right here, we slide over to the probability menu, and the 5th one down right here is random integer. So you can just hit the 5. And what you're going to tell, now it comes down to a little bit of syntax. If you do 1, 2, that's telling the calculator, hey, I'd like you to pick digits between 1 and 2. If we hit enter, it picks a 2, it picks a 2, it picks a 1, it picks a 2. One of the nice things about this function also, however, is that we can tell it, I wanted to pick digits between 1 and 2, and I want you to do 5 at a time. So if I were to change this to 1 and 10, 1, 10, it's just going to randomly pick digits between 1 and 10. And that third number will tell you how many. So if you do it this way, all of a sudden you see 5 flips of the coins. There we went tails, heads, heads, tails, heads. If we slide back here, right, we just got tails, heads, heads, tails, heads. Right? So the probability of heads in that trial was 3 out of the 5 and tails 2 out of the 5. Right? So let's say that we decided to run it again and it a few more times, right? So we could just keep running this thing over and over and over again, right? So I'll just grab these last 2. Second one, we had tails, heads, heads, tails, tails. So again, this time the probability of heads was 2 out of 5 and tails was 3 out of 5. And then we had kind of that funky one where all of a sudden it was tails, and then we had all heads, which seems a little out of the ordinary. We got 4 out of 5 heads, 4 out of 5 heads. What we should see is there's some give and take here early on, but if we started to combine all of our results, 3, 5, 9 out of 15, 6 out of 15, what we should start to see, these things are going to kind of balance themselves out in terms of kind of a 50-50 shot. And the big idea here, we've just done a bunch of experiments. That's empirical probability, right? We observed something that's happening. We're experimenting. We're playing around with it. And what we should see is in the short run, things are very random. We should have seen that in class, right? When you guys were flipping coins using the website. But what it's telling us is in the long run, large numbers is telling us that these things basically are going to settle down to the true probability. Right? For the relative frequency of repeated events, right? We keep flipping, we keep flipping, we keep flipping, even though there could be these runs in there, a bunch of heads or a bunch of tails. In the long run, eventually things will settle down to the true probability as we try more and more, as n increases. That true value is actually what's called theoretical probability, right? So the theoretical probability of flipping a coin, 50-50. So according to the law of large numbers, as we keep doing larger and larger experiments with this, flip 1,000 coins, it's going to be pretty close to 500 of each, right? Some of the probability terms, right? So we have trial. Trial is just a kind of random event, right? We flip a coin, outcome, a possible value, right? Heads was an outcome. Sample space would be the set of all possible outcomes. Here's an example. Let's say we flip a coin 3 times. So we could have an outcome of 2 heads or 2 tails. The sample space, all possible outcomes here, we'd have to list out every possible thing that could happen. So there's actually, you get all heads. If you get two heads, there's three ways to get two heads. If you look right here, right? Two heads. There's three ways to get one head. Just depends upon when the head comes, and then you can get all tails. So that's the total sample space. Another example, let's say we roll a dice. So here's all the possible. Here are some of the outcomes, right? We get 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. However, it's not the sample space. However, this isn't the whole sample space. If we want to talk about the sample space, a chart can be pretty helpful. So there's one way to roll a 2. You roll a 1, a 1. However, to 3, if you get a 3, you could roll a 1 and a 2, or you could roll a 2 and a 1. So there's two ways to get a 3. Kind of keep rolling through this thing. You get a 4, you roll 1, 3, 3, 1, 2, and a 2. You keep going through this thing, and all of a sudden we see it's 36 total outcomes. This is our sample space. That's a large sample space to write. But what I'm trying to show you here is that out of those 36 outcomes, they're not all equally as likely. You're not as likely to roll a 2 if we go up, right? You're not as likely, the probability you roll a 2 is not equal to the probability that you roll a 7. So making these charts is actually pretty helpful. So let's say the number of male children a family is planning to have. They're going to have 3 kids. They could either have 0 boys, 1 boy, 2 boys, or all 3 of their kids could be boys. Right? So this is my list of outcomes. Now let's think about all the possible outcomes in terms of a sample space. So I could have 0 boys, which would be female, female, female. There are 3 ways to have 1 boy. You could have the boy, it could be the oldest, middle, be last. You could have 2 boys. That means that the youngest is a girl, the middle is a girl, or the oldest is a girl. Finally, there have one way to have 3 boys. They're all boys. What we see, we have total outcomes, and now we start to break it down. Well, what's probably we have 0 boys? Well, there's a 1 out of 8, right? One possible outcome out of the whole sample space is all girls. We break it down. Again, you're not as equally likely to have 0 boys as you are 2 boys. So some of the properties, as you start to look through your notes here. Probabilities are always between 0 and 1. Go back and look at the charts. Nothing is below 0, nothing's above 1. There's got to be between a 0% chance happening and 100% chance happening. Total sample space should add up to 1. Not something I pointed out to you, but if you sum these up, some of that is actually 1. You go back, take a look at this one. If we were to add up all of those fractions, sure enough, the sum there is equal to 1. Here's what we call the complement rule. And there's 2 ways to write it, either the little c here or the little bar above the top. And what that tells you is basically just the opposite of something, right? The event of something occurring is 1 minus a probability it doesn't occur. Another way to think about this, the probability something occurs plus the probability that it doesn't occur is always going to be 1. Think about it this way. If I'm a weatherman, there's a 100% chance it either rains today or it doesn't. I'd always be right. So that's the idea of complement. Some of the symbols that I know you guys have seen before, but quick reminder, this is union, and that means or. When you see the word or, you're going to think add. Now, we're going to get more in detail as the course progresses, but if the events are disjoint. Right now, just go ahead and start getting in your mind. The word or means add. Upside down U, or what I see as an intersection, that means and means to multiply. And there's a rule with this saying if events are independent, but as we start this process, things are going to be independent. So how this works for us. M&M's has decided they're adding a color, brown, yellow, red, brown, all this. They do a survey, and in the U.S., 42% of the people voted purple, 37% teal, 19% said pink. So lift sample space, purple, teal, pink. So what we're going to do, let's see that those first 2 properties are actually true. Everything's between 0 and 100%. Perfect. Add those up, however, and the whole sample space is not 1, right? 42 plus 37 plus 19, right? Actually 98%. So there's this, we need a new event all of a sudden. Apparently there are people that had no preference, which means that would be 2%, right? 98% of the people are accounted for, 1 minus 1 minus that 0.98 gives us 2% of people say, hey, we don't have a preference. Over in Japan, 38% said pink, 36 teal, 16 purple. Again, add those up. 38, 36, and 16, all between 0 and 100%, sure, but we add those up. It's actually only 90%, which means in Japan, apparently a lot more people had no preference. What's the probability that we did pink or teal? Or, see that word? Think about add. So we'd add those up. What's the probability both said purple? This would be probability of purple and purple. You see the word and, you're thinking multiply. So we go grab our number, 0.16 times 0.16, 0.0256. And then finally, if we pick 3 people at a time, what's the probability at least one preferred purple? This is a little different. Actually, 2 ways we can go about this, the hard way. So if we think about it, at least one. There's options here. That means that it could be one person, or 2 people, or all 3 said purple. So there's or, which gives an indication of adding. What makes this really annoying, we're just going to call P purple. If we think about it, if we're talking about 3 people at once, the probability that one person picks it, it could be the first person that says purple, and we get 2 non-purples. It could be the middle person said purple, or we could talk to 2 people that didn't prefer it, and then finally that one. 2 people like purple. It could be the first 2 we talked to. It could be that the middle person we talked to doesn't like it, or the first person doesn't like it and the last 2 do. Or add them up, then we can have all 3 like purple. So within each of these, there's actually the probability of purple for 16%. And then so the probability they don't like purple, 1 minus that would be 0.84. But there's 3 ways to do this. So we'd have to multiply that by 3. And then we'd also have 3 ways to get purple, purple, not purple. 0.16, 0.16, 0.84. And then finally, there's only one way to get all purple, and that's just 0.16, 0.16, 0.16. So it's the grand total there would be 0.407. Now, there is a lot easier way when you hear the term at least one. And if we think about it, we can use a complement. If I tell you I have at least $1 in my pocket, if you were to think about it for a minute, what would the opposite of that be? What you would know is that I don't have nothing. You don't necessarily know how much I do have. You don't know if I have $2, $3, but you do know that I don't have nothing. If that makes sense. So the probability of at least one, there actually is a trick here. Using the complement would be 100% minus the probability of none. Those are actually opposites. At least one and none are opposites. So for us, the probability of at least one purple would be the same thing as 1 minus the probability of no purple. And there's only one way to get no purples, which would be no purple, 84%, no purple, no purple. Plug that into a calculator, you'll realize you're looking at 0.407. So it's a little bit quicker way of getting that. One thing that I would encourage you, if you ever see the term at least one, go ahead and start thinking about the probability of at least one is equal to 1 minus the probability of none.